Okay, so let's consider the situation where we have those two carts, okay, or any two objects in general. And what we're going to look at first is, let's say that there is a block or a cart of mass 1 and a block or a cart of mass 2. And they're on some kind of surface, frictionless surface, and that's going to be important. Frictionless at this point. Okay. Now we've got a frictionless surface and we've got two objects. Now let's assume that the one object pushed off the other object. So in the case before, there was an elastic sort of, or a spring sort of uh, between them, and when they cut the spring or released it, what happened was these two objects pushed apart. Now, in this situation, Newton's third law states that the forces acting on the objects are the same, but in the opposite direction. So it doesn't matter whether the spring was attached to mass 2 or whether the spring was attached to mass 1. So it doesn't matter whether it was mass 1 pushing off mass 2 or mass 2 pushing off mass 1. It doesn't matter whatsoever. The force is equal between the two of them. So what ends up happening is, let's pick a direction to be positive, like so. And let's say that the force acting on this object was in this direction. And so let's say the force acting on it was, let's say, 100 newtons. Okay. That means that the exact same force would be acting on the other object. It would just be in the opposite direction. So the forces that both would feel, so if there was a 100 Newton spring in between the two of them and it let them go and it pushed off, both objects would feel the exact same force, just in the opposite direction. You can imagine that if this was a cart and you were sitting on it and you pushed someone that was on another cart, you would think that you're pushing them, but really you're both pushing each other, because you're pushing off, and then Newton's third law says that that causes reaction force of pushing back on you. And the force is the same between the two of them. And now let's look at the situation for Newton's second law. Well, Newton's second law for the first block is M1A. And for the second one, it's M2A. And we look at that and we say, okay, well, what's the, I'll call it acceleration 1, acceleration 2, just to, give it that distinction. So the forces are the same. So what we're going to do is, what is the acceleration of block 2? So it's the net force divided by mass 1. And the acceleration of the other one is the net force over M2. Now, here's the situation. It's going to be, since F1 is in the opposite direction to the positive direction, it's negative 100 newtons over mass 1. And acceleration 2 is positive 100 newtons over some mass. Now, this is the general case, or the general situation. And that seems to make sense. I think everyone's okay with that. Well, what we want to do now is ask ourselves, what happens, if the masses, like what happens with the different types of masses that we can have? Well, let's say that the two objects, like in the previous example, were the same. So let's say they both had a mass of 10 kilograms. Okay, so if they both had a mass of 10 kilograms, 100 divided by 10 is, it'd be negative 10 meters per second. So it'd accelerate just for a brief moment in time at that rate. And the other one would accelerate at the same rate of 10 meters per second. Okay, well, let's consider a different situation. Let's assume, so another situation. Let's assume that mass 1 is extremely light. So there's still a 100 Newton force acting on it, but it only has a mass of 1 kilogram. And in the other situation, let's say that the mass is 100 kilograms. So this would be like a 1 kilogram block or cart and a 100 kilogram cart. Well, when they push off, what you're going to notice is that the really, really small one, since it has very little inertia, is going to accelerate backwards very, very quickly at 100 meters per second every second. That's incredibly fast, right? Um, that's 10 times the acceleration of gravity backwards. Whereas the other one is going to feel this tiny little acceleration forward. So the one block is going to go shooting back really fast, and the other one's just going to accelerate just a little bit in this direction. Okay? What if this was 1,000 kilograms and this was 0.1 kilograms? This one, it would be like you pushing off a wall, right? The heavier you make the second object and the lighter the other object, the one object just appears to be the one that accelerates, whereas the other one doesn't. You could take the situation of two people sitting on a skateboard. And if one person sitting on a skateboard is extremely light and the other person is extremely heavy, when they push off, the person that's really heavy will accelerate very slowly to the one direction, and the other object will accelerate very slowly backwards. Okay, so you can kind of get that idea of how important it is. But the key understanding here is that the forces are identical between the two objects. They just point in the opposite direction. And we're going to do more examples of this a little bit later. And this will lead us to the question of, like people say, well, if I jump off the earth, if I push off the earth, let's say I push down on the ground with 1,000 newtons of force. I feel the earth pushing back on me with 1,000 newtons of force. But why is it that I jump off the ground? Well, in actual fact, you are pushing off the ground. The earth has to move a little bit. Now, you don't weigh enough to cause any real effect to the earth whatsoever because the earth is so massive. But we'll do that example later on and talk about that neat idea.